Good morning, everyone. Last time we ended talking about how even though the ethylene to ethylene oxide with silver catalyst was a excellent technology, but you could not even use it for propene. And so one had to use a different method. Either you go back to the chlorohydrin based process, which generates waste, or one could actually do an oxidation with hydrogen peroxide with a titanium silicalite catalyst, which we discussed. It is a very famous process now. It is known as the HPPO process, which is hydrogen peroxide to propylene oxide. Let us now see how hydrogen peroxide itself is made. It's always good fun to keep going back. Whenever you get this answer, but how is that made? Firstly, let me tell you that hydrogen peroxide is considered to be a green reagent, as we discussed, because you end up getting water after the oxygen has been transferred. It's a moderately high volume product, about close to 5 million tons. Presently, that's what it will be. But it is going to be growing very fast because everybody is trying to look at ways of substituting some of the other oxidizing agents with hydrogen peroxide. Of course, the biggest application is in bleaching, all kinds of bleaching related applications, whether it's paper or wool or cotton. So roughly about 60% goes for that. Another is, we had seen that you can incorporate hydrogen peroxide inside soda ash, sodium carbonate, and that becomes your sodium percarbonate, which is very big for detergent industry. So that's another big area. You can see that what we discussed in terms of propylene oxide is one of the major drivers of growth. And the fourth is really that increasingly people are looking at it in organic synthesis. Wherever possible, try to use hydrogen peroxide as an oxidizing agent because it's much better than chlorine or bromine, things like that, which are relatively more hazardous. Throughout this lecture, you would have seen all the classes that every time I'm trying to give you more than one option, how something is made. And the same is true about hydrogen peroxide. This is one of the processes, not really that practiced. It's based entirely on electrolysis. And what you do is that one can oxidize sulfuric acid to peroxide disulfuric acid, this stuff. And then at the cathode, you reduce protons to hydrogen. So that's what you do. This stuff reacts with water and it disproportionates back to H2SO4, which is your starting material. So you can recycle that and you're left with H2SO5, which is known as kerose acid. H2SO5 in turn can react with water and water gets oxidized to peroxide and you regenerate your sulfuric acid. So that way it's a very nice process because doesn't really involve the generation of any waste because the sulfuric acid is getting regenerated. Effectively, what you have is hydrogen on the cathode side, which again can be utilized. The current efficiency is not bad, 70%. So it's a reasonably good process and definitely it would be in the realm of a very clean technology. By the way, the effort in electrochemical synthesis, electrolytic synthesis, they are continuing. For example, there is a membrane-based process, which I'm not going to discuss, which is discussed in this patent. I put these things in case anyone in future wants to look it up or wants to do some research, then you could do that. It's a very interesting process where hydrogen peroxide is again produced in this process. It's not very clear to me what is the advantage as compared to this. It seemed to be more elaborate, but I found this more elegant. The process that is actually most commonly practiced is based on an anthraquinone derivative. It's again, a great example of the ingenuity of technologists, how they have evolved these processes. Really brilliant people. But again, it's not such a great process because it does involve the use of natural gas. Again, you're doing a steam reforming and generating hydrogen. So the starting material is hydrogen. So you can quickly imagine that it must be some reaction between hydrogen and oxygen to form hydrogen peroxide. Now, you might say that no, this is natural gas and this process just is so clean, it uses electricity. But then if you remember that electricity is generated from coal or natural gas, and if you then do a life cycle analysis, actually the two are not that different. They are quite similar. It's just that spatially the power is being produced at a different location. That's it. But ultimately you are still using fossil fuels to generate power. Now, what this process is that one starts with an anthraquinone derivative. It's an alkyl substituted derivative. It's not simple anthraquinone. This is taken in a mixture of two solvents, a polar solvent and a non-polar solvent, and this thing is continuously recycled in the process. Okay, and I'll show you what the process is. First, the anthraquinone is reduced to the hydroquinone, so that's one. Now, remember also that the anthraquinone can also get reduced not necessarily only here, but it can also get reduced in the aromatic ring, so that you'll end up forming this structure. And this, of course, it can isomerize, and then you'll get this kind of structure. In fact, this is the chemical which is the one which is continuously being recycled. Then what happens is that once you make the hydroquinone through the reduction with a palladium catalyst, it's a slurry catalyst. So slurry system. So you take your anthraquinone in a solvent and slurry it with the catalyst. It gets reduced to something like this, and then filter it. Now, in the next step, again, the catalyst can interfere. So when you are filtering, you have to make sure that there's not even a trace of the catalyst anywhere. And in this particular reaction, the heterogeneous catalyst works well because I can separate it out efficiently. Then what happens is that they purge this stuff, this solution with oxygen. Now, the hydroquinone transfers its hydrogen to the oxygen, and it becomes H2O2. And it basically regenerates this compound, this compound, okay? And so again, you will subject it to a hydrogenation. So that's what you'll do. And the process just goes on like that. So you'll basically reconvert it to this, and the process goes on. So you've purged with air, you have formed hydrogen peroxide over here. Then you extract the hydrogen peroxide into water. Your working solution of anthraquinone and in solvent just gets recycled. Then effectively what you do is you concentrate the hydrogen peroxide. Hydrogen peroxide, as you know, has a high boiling point. So you can actually strip off the water and make it quite concentrated, something like 40 to 60% hydrogen peroxide. Okay? And then because it's a thing which can undergo radical based decomposition, you stabilize it with some kind of an antioxidant and then store it. So that's really the sum and substance of the process, and this is the more popular process. In fact, in India, this is the process that people practice. There are a couple of companies in Khanabelapur Road who manufacture hydrogen peroxide. This is one thing I know that in schools you all are taught, which is the phenol manufactured by the Hawk process. I'm just going to explain it with a little more detail, but the essence of it is probably what you have learned in school. A similar process was invented by the Russians about 2 years before Hawk. But we all know it as Hawk process. This is something you should also remember, that there are others who have done many times this work. What you would have probably known is that it is really the oxidation of cumene. This cumene. Let's look at some of the complexities of this process. As you can imagine, it's a radically initiated process. It's undergoing an air oxidation, but initiated by radicals. This radical, by the way, forms simply because it is conjugated with the ring, and therefore there's a stabilization of this radical. That's the reason why it forms. Otherwise, it wouldn't have formed, or it wouldn't have been so stable. And then it reacts with oxygen to form the peroxy linkage, and then effectively, it abstracts the hydrogen from here, and it becomes cumene hydroperoxide, and this then again gets recycled, and so it just gets propagated continuously. I mean, you are initiating it and then again regenerating it, and it goes on and on. Once you are here, then of course what they do is a hydrolysis, which is done with acid, sulfuric acid typically. The interesting thing that you must remember is that a carbon-carbon bond, this carbon-carbon bond, it migrates to the oxygen. That's effectively what happens. And then of course it sheds its water, and then this stuff is further hydrolyzed over here, and so you'll end up getting phenol and acetone. That's what you end up getting through this process. But it's not that easy. For example, once you form this radical, the question is that will the oxygen attack be faster or exclusive, or there's nothing preventing the hydrogen radical getting lost from here, and I'll end up forming methyl styrene. That's what I'll do. I'll form methyl styrene, and indeed methyl styrene is formed. So what should I do if methyl styrene is formed as a side product? Let it go waste or what? Well, you can see that if I were to hydrogenate the methyl styrene, then I'll again get back cumene, right? I just have to hydrogenate this double bond. In fact, you can see that methyl styrene is formed and it's hydrogenated back, and so I regenerate my cumene. Another reaction that can happen is that I could have a radical cleavage of this peroxy. One of the methyls will go, so I'll end up forming methanol and acetophenone. And acetophenone also forms in this particular reaction. These are unavoidable, but in some cases they have been able to successfully recycle, like methyl styrene, whereas acetophenone, they might choose to sell it as a byproduct. But remember, at the heart of this whole process is this migration of this bond from a CC bond to a CO bond. That's the most important thing to remember, and why it happens, that's also very interesting. I suppose the driving force is the formation of both acetone and phenol, both of which are quite stable molecules. So that might be the driving force. This is the main reactor where your reaction is taking place. The reaction to form the cumene peroxide. That's what you're doing. Then you're adding sulfuric acid and you're hydrolyzing it. That's how you get your phenol forming an acetone. Okay, and then you can see that I can take this stuff here. I can strip off and recover my acetone, and then I'll get my phenol. But the phenol will also have some methyl styrene. So I can pull off the methyl styrene, and that can go back here and get hydrogenated and get recycled. Then I have another step because I still have acetophenone to deal with. So acetophenone must also be taken out. So that is really done over here. I mean, after I've taken out the methyl styrene, it goes into another vessel, and then from there, I pull off and I get my phenol. Phenol distills over, and from the bottom, I take out acetophenone. Now, another thing is that in all of this, you'll see a lot of symbols. You probably are familiar with the heat exchange symbols, but there are different kinds of symbols which show up in these diagrams. What I will do is that today I will post to you an article which actually gives the list of all symbols that you're likely to encounter in in the course of your chemical engineering. So it's something good to have with you because it may not sometimes be very obvious that what is it. So it's good to have the symbols with you. Okay? If you have any questions, just let me know. This is another thing that just to show you that how sometimes innovations happen. Say I'm getting acetone as a co-product, right? I shouldn't even call it byproduct, because acetone is also as important as phenol. So somebody would have said, hey, I've got acetone, I've got phenol. What can I do with the two together? Many times, new product ideas have come actually from that kind of a question. Can I do something with the two together? Some guy must have thought of this, that if you take acetone and react it with phenol, 2 moles of phenol, you end up forming this compound, bisphenol A. It is actually a much malign compound today because it's supposed to be quite harmful. But look, no getting away. This is the biggest contributor to epoxy resins. So all epoxy resins, etc., you'll find is derived from bisphenol A. And not surprisingly, companies like Atul Industries, which is one of the largest manufacturer of phenol in the world, okay? Not in India, in the world, they also happen to make epoxy resins. It must be that they are making use of the acetone which they get. Why unnecessarily do something else with it when I can use it to make bisphenol? Okay. This is the way technologies oftentimes happen. Let me also tell you that again you have seen 2 different processes of making phenol. What I didn't tell you is that how cumene is made. It's important that we discuss it because this is one of the things you would do in the reaction block in the refinery, which is alkylation. After all, you are doing a cracking of naphtha, generating propylene, as we found. Benzene is also one of the things that you get. So it would make logical sense to try and do an alkylation of the benzene. Someone would have thought about that and therefore made cumene. Many different catalysts have been reported in the past for this alkylation, but the one that is probably today the most popular is beta zeolite. It's again an acidic catalyst that does the alkylation, and you get cumene. Now, here again, what you'll again see is this is where engineering and chemical engineers play such an ingenious role. This is your main catalytic bed where you would be putting your zeolite and putting propylene and benzene, which would be coming in. Yeah, you can see benzene, and that's where your alkylation is going on. And then I'm taking out the alkylated product from the bottom. It has several catalytic beds, like we have seen in so many cases where you have multiple beds. And then what you do is there's an excess of propene. So you recover the propene, and that's recycled back. And from the bottom, you'll take out your alkylated product. Now, what happens is that many times, because I've got actually an excess of propene, so I can also get a diisopropyl benzene, right? There can be another alkylation that takes place here, and that happens. You can't avoid it. So they end up getting a diisopropyl benzene in this, from which they might take out some of the volatiles. And what they then do is something very interesting. They take the diisopropyl benzene. This is smart, and they react it with benzene. And so what happens is that one of the isopropyl group migrates to benzene, and I can then convert diisopropyl benzene back into cumene. So that's how this recycle business happens. And so this should be one of your catchwords. Whenever you are encountering going to a factory or anything, and somebody says something and you say recycle, and then people will say how, and then you figure out whether it can be recycled straight away or you recycle it by doing some clever chemistry, like we've seen methyl styrene being hydrogenated or diisopropyl benzene being again transalkylated with another benzene. So this is your starting material. You've got your cumene, and then of course you go ahead and do your process. By the way, if you were working in a plant, what you must remember is that it is not about what I am telling you superficially, the general approaches to making these molecules in large plants. There's a huge amount of data that has to be collected. Today, of course, the best plants will have data loggers, and they'll have sensors, they'll have gas chromatographs online, and so that everything can be monitored online. But it's important that at every stage you know all the information, so that if something is going wrong, you can pinpoint where exactly it's going wrong. And so not only will you be monitoring the process parameters like temperature, pressure, vapor fraction, flow rate, all of that you'll do, but additionally all the compositional data you'll generate, so that you'll quickly come to know if something is going wrong somewhere. Okay. And I was telling you about tomorrow's technology. You see, I mean, there's a lot of work going on where, again, coming back to hydrogen peroxide, where people are seeing if it is possible to directly put a hydroxyl group in a benzene ring. Is that possible? And people, there's a huge amount of work that is going on. I saw this paper sometime back where they had reported 20% phenol conversion. Just taking benzene and converting it to phenol through hydroxylation with hydrogen peroxide, and they had used an iron catalyst, I believe. So I'm not going to go into the detail, but that could be tomorrow's technology, because that would be far simpler than the Hawk process. So never ever assume that whatever there is to know is known, and that's the way we have been taught. This is this, that. But that things are constantly evolving, and some guy will come up with some very smart process. Don't be surprised. I mean, if it happens, and I hope it will be you. One of you will do it, rather than somebody else. Now, let me tell you again, just like we saw in the case of propene, that you could not use the silver catalyst and form the propylene oxide. It had to be done in a different way. Now, similarly, there are many phenol derivatives. Like I can take catechol, which is the orthophenols derivative, or if I take the para, then it becomes hydroquinone, which we discussed. Now, those things are not made by the Hawk process. So the Hawk process is very exclusive to making phenol. Do not think that anytime I have to put a hydroxyl group in, that I can use the Hawk process. No. And in fact, the more general method, which is there, and again practiced by Atul Industries, as I told you, they are one of the leaders in the world in phenol chemistry, is completely different chemistry. What they do is that they actually sulfonate benzene. For example, they make resorcinol. That's one of their big products, because resorcinol goes in a big way into the tire industry. Don't worry about why, but it's very big use. Once I put one sulfonic acid group, then it becomes meta-directing. So I put another one in. Now this time I'll have to probably put oleum because the ring is deactivated because of the sulfonic acid group, and you require a much stronger acid. And that's the reason, by the way, as you know, I mean, these kinds of very difficult nitration or sulfonation chemistries, which required very, very concentrated acids, and actually even oleum. So that's the reason why ultimately the chamber process people got rid of, because it had a limitation in terms of the concentration of acid that you can get. But over here, with oleum, you can get, let's say, the disulfonic acid. Now, this is again very interesting, that they actually do a fusion chemistry. So you take this and at a high temperature, something like maybe around 250 degrees or so, you cook it up with caustic soda. So it's an alkali fusion that is taking place. The driving force for this reaction, and some of this is very interesting. Otherwise, if you thought that how the hell do I break this carbon sulfur bond? It's quite a strong bond, not so easy to break. But what happens is that when I react it with sodium hydroxide at high temperature, actually an SO2 group comes off from each of these, and the SO2 reacts with sodium hydroxide to basically form sodium sulfide. So the driving force for the reaction one is of course that I'm doing it at elevated temperature to manage the kinetics, and the second is it must be the formation of a very stable compound, sodium sulfide, not as stable as sodium sulfate, but nonetheless a very stable compound. So when you are looking at the thermodynamics of some of these processes, don't ignore the other things that are formed. I've seen too many people doing very, very density functional calculations on this, that, and trying to show stabilities and all that is great. But you've forgotten that this also you form something else, and which is also providing you a drive. Just like you'll see, in fact, when we discuss battery, something similar. So this chemistry is completely different from the Hawk chemistry. And at the end of it, you're ending up with this. Now, obviously, this is not required in the case of phenol. So probably they will not necessarily use it for phenol, although they might. You see, if they are basic in sulfonation chemistry, then I might as well also make phenol that way. I can do it. But sometimes, it is difficult to control just a mono sulfonation. So, sometimes because of those reasons, they might prefer to do it by the Hawk process. And if they are, if they want the acetone for making epoxy resin, then I'll do it by the Hawk process. Let's go to another, and this will be the last petrochemical that we will discuss. And this is again something very big and very important for dyestuff and polyurethane, which is basically nitrogenous aromatic, things like amino or nitro, and things where I can diazotize and make dyes. All the different dyes are diazo compounds, so many of them. Now, what is interesting is that because I talked to you about phenol, I thought I'd link it up. You can actually do a transamination. You can take phenol, react it with ammonia. Only thing is you need a large excess of ammonia, something like about 5-fold excess, okay? And it forms aniline. Okay? And the beauty of this process is that all I get is just water, as the side product. This work must have taken a long time to identify oxides of magnesium, boron, titanium, supported on alumina or zeolite. And not only that, then they have a co-catalyst, which is vanadium or tungsten. This is the kind of trial and error catalyst development that takes place. Nobody will be able to predict this theoretically. I don't think so. This will have to be done by trial and error. Okay? So there's a company, Aristech, which is, for example, manufacturing aniline by this process starting from phenol. In India, of course, I have not seen this process being practiced. It's more of the linear process which is still popular, which is that you take benzene. Easier to probably understand in some ways. It would be more of the kind of high school chemistry that you've learned. That you do a nitration, and remember, nitration is not done just with nitric acid. It's done with a mixture of nitric acid and sulfuric acid concentrated. I believe it is because it forms the nitrosyl sulfuric acid, and so the nitrosyl group becomes relatively more positively charged, and so it will be good for doing the aromatic substitution reactions. So that must be the reason why that is done. So they end up doing nitration, and then the nitro compound is further taken with hydrogen, and they do a Raney-Nickel catalyst-based reaction or some other catalyst perhaps, and they form aniline. It's not a very exothermic reaction, very mildly exothermic. And I've given over here the process, which I'm not going to go into how you exactly do the hydrogenation, because hydrogenation will form water. So you need to get rid of that water and then do a further purification, and you can get very high purity aniline, something like close to about 100% purity. Of course, nitrobenzene is a more basic chemical because that is what is then taken for a lot of the dye stuff processes. But 80% of aniline production actually goes into the manufacture of polyurethane, and this is the most important monomer for polyurethane. It's methyl diphenyl isocyanate, okay, MDI. You react aniline with formaldehyde. This is a very nice way of introducing this. The analogy of this would be reacting it with acetone, which we found for making the monomer for epoxy resin, bisphenol A. But otherwise, if you don't want substituents here, then you react it with formaldehyde. Remember how formaldehyde is made, which we have learned, and that's what you'll get. You'll get the amino first of this product, and then that has to be reacted with phosgene, to make the isocyanate. Now, I must also tell you that there's a huge amount of work going on in the world on trying to find non-phosgene routes for introducing isocyanate routes. You would have even seen in the Bhopal tragedy, the use of phosgene and methyl isocyanate production, and so that's been very common to use phosgene. But ever since the Bhopal disaster, people have been trying to get out of phosgene, and so this is one of those reactions where you can take aniline, react it with this compound called dimethyl carbonate. You end up with this, and from which you can derive the isocyanate. In fact, this is a big area, and in turn, that dimethyl carbonate can be produced through reaction with hydrogen peroxide. So again, hydrogen peroxide could become extremely important if methyl carbonate becomes important, and basically to make these things, the isocyanates that way. And so sometimes some of these technologies can completely alter the demand for certain chemicals. So the most important take-home message that I want to leave you with is that in every case, almost in every case, and I have chosen processes so that I want you to see it as an evolving process. Every case, you have seen that there is more than one process. And it's not as if things have come to an end. The efforts are continuing. People are constantly trying to see whether either the existing processes can be improved through incremental innovations or through radical transformations in technology, like when you come up with something like the silver-based ethylene oxide process or the Hawk process. I mean, these are radical shifts in technology. And so, or the anthraquinone process that you saw. So these are very interesting examples of that. Today was supposed to be a 1-hour lecture, but then Ria told me that you all have a free period after 11:30, and she suggested that I could continue for 1 more hour. So I'll take that opportunity to introduce you to batteries and probably discuss a bit about the invention of the lithium-ion battery, for which the Nobel Prize was given in 2019. I wouldn't be surprised if a lot of you end up working on batteries, because as people are talking about renewable energy and renewable energy is intermittent, you'll have no choice but to have batteries. And if you're going to have electric vehicles, which people are talking about, then again you need batteries and lightweight batteries, powerful batteries. Okay, so battery is going to become extremely important, in the coming years. It already is. I think that all of us who use a mobile or a laptop and you are traveling, it's all running on your battery, and you know how important it is. Just in case some of you don't know, the origin of the battery is really in something known as animal electricity. And this, you can see 1780. This is a very famous experiment done by Galvani. He took the leg of a dead frog and happened to connect two wires to that frog. And it was almost as if the frog jumped out of the table. He really woke up with a shock and said, "Hey, the frog has come alive." And that he termed as animal electricity, because he really thought that the animal did something very magical to generate electricity. Later on, what they realized was the animal is only supplying electrolyte. Because it was not completely a dried up dead animal. It probably was a freshly killed animal or mouse or something, frog. And they connected up the legs of that frog with this wire. So one was that it was an electrolyte, but still, why was it jumping? What happened? And then later on, they found that the clips which they used for the two wires were different, of different metals. And so what that meant is that I could generate an EMF. So it was like a battery. This was actually recognized by Volta. And in fact, Volta then quickly went on to make a battery from zinc. And Volta became so famous in Italy that the government over there donated a temple to Volta, because people realized what important discovery the whole thing was, and the invention of the battery. Volta then was able to also make the voltaic pile, where he put many of these cells in series, pile of them, and also in some cases he probably also connected them up in parallel, that he could generate large voltage and current, from these units. We now know that what did he use? He used zinc and copper as the two metals, and he had a electrolyte. Probably, I'm not very sure what he used, but maybe sulfuric acid or a salt solution or something of that sort. So we know that zinc is more electropositive, and so zinc will go to zinc ions, and copper 2+ will get reduced to copper. If you now add up these two equations, you're generating 1.1 volt as your potential. That's the voltaic pile. Now, again, I must tell you that you would have heard of the electric eel, which can give you a tremendous shock. And the voltaic people actually studied, the electric eel, and what it has is just like a voltaic pile. It has got thousands and thousands of cells, dish-shaped cells, each of them generating a tiny EMF, but cumulatively they can give you a massive shock. Now, after that, of course, as you know, Faraday, of course, came up with the laws of electrolysis, and effectively saying that like for example, the amount of copper that you deposit will be proportional to the amount of coulombs of charge that you pass, and secondly, it will also depend on the equivalent weight. So if it's a 2-electron process, you have to divide the atomic weight by 2, just so that you've got the concept of equivalent weight. You deposit things as per the equivalent weight, so to take care of the multi-electron processes. The other thing which you need to remember, when you are talking about batteries, the most important things to remember, one is that how much charge does a battery store? So that is your charge capacity, just the coulombs of charge that your battery is storing. Energy stored, Of course, I have to multiply my charge by my voltage. Then only I'll get my energy, and it will be watt hour. So I've got volt into ampere. That will give me my joules, and so I'll express it as watt hour as my energy. And my specific energy is obviously people are trying to make lightweight batteries. How much energy have I got in my battery, and what's the weight? So I just divide by the weight, and then I'll get my watt hour per kg. That's my specific energy. Sometimes there's space constraints in a battery. It's not just weight. If you make the battery too voluminous, it may not fit in, and so the energy density becomes important, which is the energy divided by the volume of the battery. Then specific power is extremely important. I can have all the energy in a battery, but how rapidly can I make it deliver? That's power. Like if I'm starting my car in the morning, or when it's very cold, sometimes you'll find your battery's gone dead. It cannot deliver the amount of power that your car requires to start. So specific power is extremely important. And that would be what? Watt per kg. Then there's efficiency. Like for example, after all, if I'm taking a rechargeable battery, for example, and when it's going dead, again you put it into the bucket and you're charging up the battery. So how much charge did you put into the battery at the time that you charge? You don't know because we don't have those meters. And then when I operated the battery, how much of the charge did I get out? So that is my charge efficiency. What was the ampere hours that I put in at the time of charging, and what percentage of that I got out when I was using my battery? Energy efficiency, just that's charge. That's only Coulomb. But actually what you want to know is really the energy efficiency. How much energy did I supply to the battery? Obviously, it will depend on what was the voltage of your battery pack which you used and how much charge actually flowed. Okay, so voltage times ampere times time, the duration, and that is your watt hour. So that's again very important. How much am I getting out of it? And finally, another which is very important is the self-discharge rate, which is that you'll find that there is inevitably some amount of leakage that takes place and the battery discharges. Different batteries are good in that sense. Some of them discharge much faster than others. Okay, but that is known as the self-discharge rate. Like it happens, no? You've left your car and gone off on a holiday, come back after a month, and no, you can't start the car. Battery weak ho gaya. Remember another thing, that a battery's performance also depends on to what extent am I discharging or draining out my battery. Let's say I'm at the careless type, and every day your mobile is going dead, and you say, oh, my mobile is gone. Now I have to again start from scratch, from zero charge. It has to be charged up. That's known as a deep cycle. The more number of deep cycles you have of charging and discharging, the more rapidly your battery will deteriorate. Ideally, you should make sure that you are recharging your battery when you have got at least 20-30% power left. That's what ideally you should do. There are other things that you need to remember. One is, of course, the innate nature of the battery, but then you have to, batteries are very dependent on the ambient temperature. How you operate them, that is whether I'm discharging them fast or slow, that will have a huge effect on the performance of a battery. What is the charging methods that you use? Like for example, if instead of let's say plugging it into a 12-volt adapter, suppose I just straight away put a 120 volt or 220 volt line. Can you imagine what will happen? There'll be a surge of current, and because of that, there'll be a heating up of the battery, because every battery will have an internal resistance, and so when I've got more current flowing, the heat that is produced is I squared R, and so there will be a heating, and your battery might get completely damaged in the process. All clear?
Yes, sir.
Okay. I told you about charge efficiency, and also that if you drain out a battery quickly, that you'll get high power. But let us see what is the effect of that. Now, what happens is that one is that any battery will have an intrinsic ampere hour of charge capacity. What we actually measure when we say so many amperes hours is under typical conditions of operation. Like for example, suppose let's say I'm operating a battery for 10 hours, and basically the battery is supplying 1 ampere of current. I could also have another case where I'm operating the battery for 1 hour, and I'm actually taking 10 ampere of current. The question is, we think that the two would be identical, right? Because total amount is 10 ampere hour, but that's not the case. That's not what happens in reality. You will not get exactly the same 10 ampere hour in the two cases. Your battery will wear out faster in this particular case. This was actually recognized by this person Puchard. Puchard basically was playing with the concept of what is the innate, intrinsic amount of charge that I put into a battery. When let's say I've connected it to a power supply, out of that, how much am I getting out? So he wanted to actually estimate that, and he came up with this equation, which is known as the Puchard capacity. This thing, it is just basically the current that you are actually the battery is supplying, and then to the power k, and k is a coefficient that he developed, I to the power k, and k depends on different types of batteries. It's not the same for all batteries, and multiplied by the time. It's like ampere hour, but except that there is a to the power k term which comes in. For example, in the lead acid battery, they have worked out the value of k is 1.2. So if now, let's say I say that there is a battery which has a nominal capacity of 40 ampere hour at 5 hour rate, means that I can calculate that it operated for 5 hours and I got 8 amperes of charge from this battery, because I can do I is equal to 40 upon 5 is equal to 8 ampere, which is the experimental data. So this is the experimental data of how many ampere hour I actually got out when I operated it at 5 hours. Now, when I plug this into this equation, into this, and so I'll now get 8 to the power 1.2 multiplied by 5 hours, and 8 is my ampere, and it comes to 60.6 ampere hour, which means that actually the battery had 60.6 ampere hour of charge in it, and I only got 40 ampere hour out of that. So you can work out. So your charge efficiency is what? Is just about 2/3, means about 67%. So the total amount of charge that you put in, I didn't get all of it out. And if, for example, I know the voltage that I supplied at which I charge, and then I know the voltage at which I am drawing the current, and if I now try to get the energy efficiency will be still lower. So this gives you an idea of what is meant by Puchard capacity. So the innate capacity of the battery was 60.6 ampere hour, out of which I got 40 ampere hour when I operated at 5 hour rate. If I had operated it at 20 hour rate, I may have got 50 ampere hour instead of 40 ampere hour. It just depends on the value of the K. Here I have told you that the value of K was given at 1.2. But suppose I didn't know that, and you're working on battery research, and someone tells you that, hey, I want to know what is the Puchard capacity of the battery. So what you can do is that if you can generate data for two different conditions of operation, then I can actually get the Puchard capacity. For example, they're showing over here that they're taking a battery and they're getting a 42 ampere hour rating when they are discharging over 10 hours, which means that the current would be 42 divided by 10 means 4.2 ampere. And when they did the same thing, where they drained out the battery in 1 hour, what they found is that the ampere hour is 33.6 ampere hour. Here, therefore, my time is 1 hour. Okay, and what will be my current? 33.6 ampere hour divided by 1, which will be 33.6 ampere. So I've got my values of current and time at the two different values. So I can get I1 is equal to C1 by T1, I2 is equal to C2 by T2. And now I've got these. If I write the Peucat capacity equation, what will I write? Cp is equal to I1 to the power k multiplied by T1, and the other one Cp will be equal to I2 to the power k multiplied by T2. The Peucat capacity is the innate capacity, that's the intrinsic capacity. So that is not going to change. And therefore I can then equate these two equations. So I'll write I1 to the power k into T1 is equal to I2 to the power k into T2. And then I can collect the terms, take the logarithm, and then I can express k. This should be small k. It's log T1 minus log T2 upon log I1 minus log I2. That's what it will be. And I just put in the values because I know all the values. Current is 4.2 ampere. Over here, current is 33.6 ampere. So I plug in the values of time and current. I can get the value of k. K is equal to 1.107. You can work it out. And now I've got my value of k. I can put in into the equation for Peucat capacity. If I take any of the examples over here and work it out, it will be the same for both. So Cp is equal to, let's say, if I do this 42 ampere hour at 10 hour rating, so I'll have 4.2 to the power 1.107 multiplied by 10, and that's equal to 49 ampere hour. So what it's saying is that my intrinsic capacity was 49 ampere hour. Out of that, I got 42 ampere hour when I operated over 10 hours with a lower current flowing. And when I tried to operate it over 1 hour, discharging very high current, then it comes down to 33.6 ampere hour. So that's what it is. So what that also tells you is that obviously the efficiency is going down as I discharge faster. But then when I'm discharging faster, what am I doing? I'm actually I'm also getting a high power, right? Because I've got a higher current, and let's assume my voltage remains constant. The watt per second will be more in this case. So I'll get a higher value of power, but I'll get a lower efficiency, energy and charge efficiency. And that's exactly what is shown in this kinds of plot. It's known as the Ragon plot. I took this from a German publication. That's why some of these are in German. And what you can see is that this axis is power, watt per kg. This is the power density. And this is your specific energy, watt hour per kg. So if you try to operate the same battery delivering a higher power, I'll end up with a lower specific energy. That's what it will be. So that's what this thing says. There are cases, like for example, you can take these are known as supercapacitors, where what I want is I want a fast instantaneous power. So you can see, these things can deliver very high power, but extremely low specific energy. So, it just depends on where you like to make the compromise in your operations. But it's very important that you know this, because, a lot of people talk about, hey, electric vehicles, it's so good, so clean, I'm doing this, doing that. Have they done all these calculations? Do they know what are these efficiencies? So it's obviously extremely important that you know this. So as all of you know, there are two kinds of batteries. One is the primary battery, which is the disposable battery, which we use in our mouse or in a torch cell, which you put in, and then once it goes dead, you just replace the battery. So that's your primary battery. Secondary battery is the rechargeable battery. Obviously, from a sustainability point of view, naturally a rechargeable battery is far superior. You can run your mobile battery for 2-3 years at least, and the battery is fine. It's every day you're charging, discharging, doing so much of work with it. Whereas I find every 20-25 days I'm replacing my battery in the mouse. So obviously this is much more sustainable, a rechargeable battery. The other thing that you need to know is that batteries traditionally which were developed were all aqueous batteries. It may have been even a paste type of thing, but it would still have some kind of a water-based composition. Then you have the non-aqueous battery. That's where your this famous lithium-ion battery comes, and its predecessor, the lithium battery, which was a primary battery. These are all non-aqueous batteries because obviously you cannot have lithium in contact with water. It will immediately evolve hydrogen, right? And it will catch fire. So people had to then understand the entire concept of battery design in non-aqueous systems. But all your things like ionic conductivity of your electrolyte, etc., all remain because I have to maintain continuity of circuit. I have to have ionic conductivity in my cell. So obviously these non-aqueous batteries have electrolytes which are also ionically conducting. I will discuss now only the rechargeable batteries, and but I've also listed out here some of the most famous primary batteries, starting from the Leclerc cell, which was so famous. And then, of course, you have many other batteries which were subsequently developed. Anyone who wants to read up more, you can read it up. The entire revolution of rechargeable battery began with the lead acid battery, which was invented in 1859. So you're talking about what? You're talking about 163 years have gone by since the invention of the lead acid battery, and the battery is still going strong. Notwithstanding all this talk about lithium-ion battery and the revolution of the future and all, truth of the matter is even today, all our batteries, I mean, if not all, the majority of it are lead acid batteries. All the solar energy storage today in India is all lead acid battery. So, lead acid batteries continue to be very important. And just let's look at the half cell reactions. So if you are discharging the battery, say it's in a charged state, one electrode is lead, this is your anode, and the cathode is lead dioxide, PbO2, means lead in the +4 oxidation state. When you're draining it out, you're discharging it. What is happening is reacting, the lead is releasing 2 electrons, goes to its preferred oxidation state of lead 2+, is combining with a sulfate. Your electrolyte is sulfuric acid and is becoming lead sulfate. But you can see that sulfate from the sulfuric acid is getting consumed here. What's happening at the cathode? Your lead dioxide is also becoming lead sulfate. This is the reaction. And what is it doing now? It's taking 4H plus 1 sulfate and it's forming lead sulfate and water. So what did I do? I consumed 2 moles of sulfuric acid and in turn generated 2 moles of water, which means that I diluted my electrolyte. So this particular cell would obviously be dependent on the Nernst equation and the concentration term of the Nernst equation, which is E is equal to E0, and then you'll write your term with ln C1 over C2. So what is happening is that the lead acid battery will not give you a constant voltage. Its voltage will keep dropping. And that's the reason why after some time, sometimes people will say that sometimes, of course, the battery goes dead. And even while it's operating, over a day, it can get weakened. When you're doing the charging, now you're obviously supplying power from an external power supply. And what are you doing? You're just reversing things. And so what was my cathode now becomes my anode. And because I have to convert lead sulfate back into lead oxide, so I have to and release electrons. Those electrons are flowing into the what now has become my cathode. This has become my anode, and at the cathode, my lead sulfate is again picking up those 2 electrons, becoming lead. So I've just got this back, and so that's what the charging and discharging cycle is. You can also see the half cell potentials of the 2, and so if you add these up for these half cell reactions, that's the cell potential. It's about 2.15 or 2.2 volts, which is what a lead acid battery will provide. You also know that lead has the problem that it's very heavy. So obviously the battery will be very heavy. And you've also got large amounts of sulfuric acid, and all of that will add to the weight. And so in terms of energy density, the lead acid battery is not so good because of the high atomic weight of lead and also because of the bulkiness of this overall battery. Now, take another case, which is one of the most famous batteries which was developed. It was really originally developed by the Europeans, and later on a variant of that, which was the nickel iron battery, was popularized by none other than Edison, and that was known as the Edison battery, nickel iron battery. And in this, the nickel is in a nickel +3 state. So it's a cathode in the discharge cycle. From the +3 state, it basically goes to the +2 state, which is nickel hydroxide, and releases OH minus upon reaction with water. Where did this electron come from? It came from the cadmium, which was the anode. So the cadmium gives off 2 electrons and it becomes cadmium hydroxide. So if I multiply this by 2, I'll be able to write the balanced equation as cadmium plus 2 nickel oxyhydroxide plus 2 water going to cadmium hydroxide plus this. That's what I've got. Now, what happens is that in this, you are forming hydroxide and you are also consuming hydroxide. And so there is no change in the concentration of the alkali that you take in the electrolyte during the operation of the battery. And therefore, this battery, you can add up the half cell potentials, comes to about 1.22 volt, which is what you've got over here. And this battery, therefore, gives you a very stable output of 1.2 volt throughout, because all the rest is solid. Okay? These are all solids. They will not come into your Nernst equation. And so, because there is no real change taking place in your electrolyte, so effectively, the battery voltage remains quite constant. So, this in a way is an ideal battery. And that's what you want a battery to do. You want a battery which will live long. It will also give you a very, very constant voltage and current when I'm operating. And when, of course, finally, all my cadmium got consumed, I know I have to recharge and the battery will suddenly go dead. So in a way, this is really the most ideal performance of a battery. In fact, it's not very different from human beings. After all, what do we want to do? We want to live long. We want to have a very healthy life. We want to be able to jog till the last day, maybe. And you're gone. No ICU business. And you're dead. And that's the best way to die. Nobody felt any pain. I mean, relatives will feel, but the person didn't feel anything. Just died. And otherwise lived a wonderful life throughout. So there is an analogy between a good battery and how we want to live. Okay. Now let's go to the non-aqueous battery. This was the first non-aqueous battery which was patented by the Japanese. It's sad that these people from the Matsushita company who developed this battery in the late 60s did not get the Nobel Prize, because I feel that a lot of their ideas were subsequently copied, by all these other guys who won the Nobel Prize. I don't want to undermine what they did. They did something extremely important. I don't want to undermine that, and I'll discuss that. So the first thing that what these people said is that lithium, obviously you can see the atomic weight is just 7, and what kind of a oxidation potential it has. It's the most electropositive element, lithium going to lithium plus. So tremendous amount of power can be generated from the lithium as an anode. Of course, they had to solve the problem that what is my cathode. So what they did, and this is a primary battery, so they were not making a rechargeable battery. This went dead after operation. So what they did was something extremely clever. They took carbon, okay, like graphite, and they fluorinated the graphite. And then what happened was that at the anode, lithium went to lithium plus and released an electron which flowed in the external circuit, came to the cathode. And in the cathode, what I did was that because fluorine is so electronegative, so once it gets the electron, the fluorine becomes fluoride, and this carbon just goes back to being carbon. Okay, it just becomes regular graphite. Why is that important? Because lithium and fluoride then combine to form lithium fluoride, and you can imagine the lattice energy of lithium fluoride. So there's a massive driving force for this particular operation of the this particular battery. So this is the first time they were able to actually make a battery which gave something like about in excess of a 3-volt voltage output, which none of the other batteries, whether it's nickel, cadmium, or lead acid, none of them could do. So you got an extremely high voltage. Second, as you can see, is that the current was quite flat under some conditions of operation. And so it's almost like what I was telling you, that it's absolutely flat and then precipitously falls, which is a most ideal kind of an operation of a battery. The other thing is that they had to solve the problem of the electrolyte, because I've got my anode, I've got my cathode, that's fine. What about my electrolyte? So they realized that it will have to be an organic solvent, and it cannot be something that reacts with your either your anode material or your cathode. So they were able to develop such solvents, which were I can't remember what was the solvent they used. Maybe something like propylene carbonate or something. We'll see. Okay, and but the solvent per se is not ionically conducting. And then they started looking at salts which have a solubility in that organic solvent. And they found there are salts which can dissolve in that organic solvent, and not only dissolve, it can dissociate so that it can conduct charge in the solution. So that is the first lithium battery which was made. Then came these three people who got the Nobel Prize in 2019, and this person is the oldest person to ever get the Nobel Prize. He must be about 99 now. This person, Stanley Whittingham, I will consider as the brain behind the lithium-ion battery. He was the one, he and his basically supervisors, his guide, who did some remarkable work. I would really put him at the heart of it. And these were the people who did some great work to improve the performance of the battery. And Yoshino, he was actually working in an industry, I think in Asahi Glass, if I'm not mistaken. At the end of it, I think the biggest contributions was that Yoshino developed the right anode material and good enough developed the right cathode material. And this person actually was the initial promoter of the concept. Up till now, what you have learned about in a battery is in all of these batteries, what do you see? That there is some redox reaction that takes place, right? Cadmium goes to cadmium 2+, lead dioxide goes to lead sulfate. Okay, so it's some redox couples which are changing, but you can also do reactions where actually the redox processes that are taking place are the ones taking place in the electrode, and there is no redox process which is really taking place in the electrolyte. So it's a very interesting concept. Let me try and explain to you what I'm talking about. And this is really initially owed to Stanley Whittingham. What they did is that they made some layered materials. They've got reasonably good electrical conductivity, these materials. things like lithium, titanium sulfide, lithium cobalt oxide, lithium, vanadium selenide. So these kinds of layered materials. The early work was done in Oxford on these kinds of materials. And what they found is that lithium has a remarkable property, or these materials have a remarkable property, that lithium can slip in and out of these materials. Now, when would lithium be there and when would it not be there? Let's try and understand. If I write LiCoO2, what is the oxidation state of cobalt?
Sir, 3. Cobalt
Yes,
is 3.
correct. 3. Each oxygen is 2 minus. So I've got 4 minus. Lithium is 1 plus. So obviously cobalt is cobalt 3. Now imagine a situation where I'm oxidizing cobalt and it's becoming cobalt 4. Do I need the lithium now?
No, sir.
Absolutely. So the lithium will get out of it, of this place. And so that's what I mean by lithium coming in and going out. It will depend on what is the oxidation state of my cobalt. Obviously, what you can imagine is that, I'm being very simplistic, and where in fact a lot of fundamental computations you might want to do come in, is that there is an activation energy. For example, do these things have to prop apart a bit? What happens? Do they collapse and prop apart every time there is lithium? Because if that happens, then there will be an activation energy associated with that. Okay, and that's where all the calculations, understanding solid state structure, etc., becomes so important. This is typically the Fermi level diagram of, let's say, a battery. Suppose I'm discharging my battery, like when I'm operating my mobile. What am I doing? My electron is going from here and it is going here. So this is the total potential that I'll get out of the system. And so the higher this thing is and the deeper this thing is, obviously I'll get more and more voltage out of it. That's it. And that's what happens with your half cell potentials. You can even understand based on a half cell potential. Okay, so what basically Goodenough did and what Whittingham did is that both of them developed the cathode material, which I showed you. Cathode means during discharge, what is the cathode? So what effectively was the big contribution of Goodenough was that the cathode material, which originally was developed by Whittingham, which was at this kind of a Fermi level. So it would have been somewhere here. So I got less voltage out of it. What Goodenough did was that by introducing the cobalt 3 plus, cobalt 4 plus system, he buried it deeper over here, and therefore, my voltage increased. So he was able to double the voltage output from a lithium-ion battery, which initially was something around 2 volt, and Goodenough made it about 3.5 volt or thereabouts. That's what he did. The first time someone had shown that carbon can be made negative and lithium can go back and forth into carbon, just like in the case of those cobalt oxide and titanium sulfide, was a person called Yazami. This person, poor guy, he doesn't figure anywhere. And he made this with graphite, and he was able to show that exactly as in the case of the cobalt oxide, lithium can go in and out from graphite because graphite is also a layered structure. What really happens? What is the thing that is going on? Be careful about this negative and positive electrode, because it depends on what cycle you're talking about. Are you talking about discharge cycle or charging cycle? When I'm talking about negative electrode, we are talking about discharge cycle. What will happen is that it's my negative electrode. It's got electrons over here, which are counterbalanced by lithium. Now my cobalt, it's not exactly in the +3 state. It is somewhere between a +3 state and a +4 state. That's what it is. Now, discharge, you can see it is going this way. So electrons are being lost from this. So now the lithium will want to migrate. Lithium leaves, And what's happening over here? The electron which I lost over here is being taken up by my cobalt. And so my cobalt is becoming more like my cobalt 3 over here. And therefore, now it needs the lithium. And so lithium, which was lost from here, is finding its way over here. So if x got lost, then 1 minus x plus x becomes 1. So I've got 1 lithium over here. So I can write this during discharge that these two effectively ended up being this. And when I'm charging it up, I'm doing exactly the opposite. I'm pushing electrons into my carbon and I'm taking out electrons from my cobalt, and it is basically going into this. That's effectively what is happening. Obviously, we have not talked about the ionic conductivity. Lithium cannot just hop around from anode to cathode without any electrolytic conductivity. It needs electrolytic conductivity. Maybe before the other electrode, I'll come to the electrolytic conductivity. So the solvent which is used in the lithium-ion battery are basically things like propylene carbonate, ethylene carbonate, methylene carbonate, methyl carbonate. So these are the ones that are used. And they're not used just in pure form. They use a mixture, and they use this as an electrolyte, lithium hexafluorophosphate. So this stuff very nicely dissolves in the solvent and it dissociates. And the interesting thing is the electrolyte also has lithium. This also has some lithium. This also has some lithium. And in every case, the lithium is in the lithium plus state. The lithium is not undergoing any change. Lithium is not becoming lithium metal. The carbon is becoming negatively charged. Or the cobalt is changing its oxidation state, not the lithium. And that is why it is known as lithium-ion battery, because the lithium remains as lithium-ion throughout the operation, whether you are doing charging or discharging. The electrolyte, what it does is, obviously it helps with the ionic conductivity, and the solvent, like let's say this is my lithium ion from this electrolyte, and this is my PF6 ion, hexafluorophosphate, and the lithium ion gets nicely solvated by these, and this also helps to keep these ions apart, and also it keeps it very stabilized. So that's what happens. And of course there will be an exchange, like this lithium might end up here, this lithium might end up here. So it's not as if the lithium from here will necessarily jump here. I mean, there's lithium all over. There'll be some over here, some over here, some over here. So that's how they move. Now, what you also must remember is that you have to try and reduce the internal resistance of the cell. Otherwise, there will be a voltage drop across your cell. So what you have to do is that, anything which can cause a problem, like for example, if I need to expand these lattices, then there's a energy requirement, so I'll lose some. If, for example, there are frictional forces between these molecules as they are sliding past each other, there would be a problem. There would be heat loss. So what some of these solvents are designed for is that they almost become like lubricants. They are very well lubricated, and so that they glide past each other with minimum frictional loss. And so that's the kind of design. But what Yoshino showed was that, you see, every time this graphite is becoming negatively charged and positively charged, the solvent which I use, this solvent, actually gets incorporated into the graphite. And gradually, the solvent is degraded. It means that some redox processes probably took place along with the solvent. And what they found is, the battery had dried up. There was no solvent after some time. And Yoshino then didn't abandon the graphite, but he started playing with the material properties of carbon. And he started looking at all kinds of carbonaceous material, and was able to finally find a carbon somewhere here, which actually ended up being superior to graphite in the sense that there was this carbon did not interact with the solvent. It left the solvent stable, which Yazami never worked on. It was Yoshino who did that. So Yoshino contributed towards the carbon, which serves as the anode in the discharge cycle, and good enough really developed the cathode material, the cobalt oxide. And Stanley Whittingham is the one who first found out about how lithium goes back and forth in these lattices. Let me also tell you about two other innovations. One was, you see, what happens is, although we have written that it is the carbon which becomes negatively charged and the lithium remains a lithium plus, but actually that's not true necessarily. Some amount of lithium plus could actually also get reduced to lithium, because it's not a matter of joke to reduce carbon to carbon minus. Under those potentials, even lithium plus might become lithium. And what happens is that it was found that, when lithium plus, let's say during the charging, becomes lithium, then that lithium which I used originally, which may have been in the form of a flat sheet, it doesn't remain like a flat sheet. It forms like dendrites, like whiskers of cat. And those whiskers can go and penetrate to the other side. From here, it can go and short circuit the whole cell. And because of that, the whole thing can catch fire. This was a huge problem. What Yoshino did, I don't know if Yoshino or some other person in his company, I'm not very sure who did this, but they did something extremely clever. What they did was, they introduced a spacer, a separator. And the separator happened to be just a film of polyethylene. The polyethylene was not just a film of polyethylene, it was a very, very porous polyethylene. Big pores, not small. So that there is no problem in these electrolyte, solvent, etc. moving in and out of this separator. It was free to move as they wish. But in case there was a short circuit and it generated a lot of heat, then what happened is, because it's a fairly low melting material, this polymer, say around 80 degrees it will soften, or even at lower temperatures. So this film, which was very porous, it melted and it blocked off all the pores. It became non-porous, this stuff. Moment it became non-porous, what did it do? There is no more redox process that can occur, because things cannot move from the anode to the cathode or vice versa inside the cell. So it cut off the cell. So in a way, what was it? It was a fuse. But we are all used to our fuses being somewhere else in a fuse box. What these guys did is they had a built-in fuse over here, which effectively kept the thing safe by this simple innovation of just taking a low melting porous polymer film, and when it heats up, all these pores collapse and it completely seals it up, and there is no migration of any constituent from anode to cathode or vice versa. And this is one of the biggest things that has helped in improving the performance of and the safety of the lithium-ion batteries. Another was that, very simple, you see, although these materials were quite conducting, they were not that conducting. So what they did was they used some plates over here. These plates were basically known as collectors. I think this was invented by the Koreans. I'm not sure. And the material, whatever we are talking about, this cobalt oxide or carbon and this, is actually coated on these collectors. So these are like my primary electrodes which are conducting the charge. And from there it is getting transmitted to this, and then the rest of the chemistry is happening. Now, just to give you an idea of how amazing this was, this development. If you look at the specific energy of a lead acid battery, this is the value 20 to 35. This is about 90. In fact, the energy density is about 153. In fact, today it's a lot higher. I think it's closer to about 150, this value. The voltage is 3.5, and I can generate a good deal of power from this particular battery. Earlier, it was used only in very small cells like mobile, laptop, etc. But today, ever since Tesla introduced it in electric vehicles, lithium-ion battery is no longer about small application. They have even run trucks with this kind of battery. Another great thing about the battery is that the self-discharge, which I talked to you about, is much lower here. It's about 10% per month. I think today it's even less because this slide is quite old. Whereas the lead acid battery, every day it would lose about 2%. So you're talking about 60%. So this is about 6 times better than that in terms of self-discharge. It lasts much larger in terms of the number of cycles of charging and discharging that you can do. And another great thing is that once your battery is drained off and you have to recharge it, the lithium-ion batteries can be recharged faster than you can recharge the lead acid battery. And let me tell you, today people are trying to go to something like 10 to 15-minute charging, because if you take your car to a garage, or to a petrol pump or whatever that equivalent is, and if it has to be charging there for hours together, then how are you going to charge so many cars? You'll need so many points. So obviously, this is the big area of research, rapid charging. Finally, just one more thing you can see, and for chemical engineers especially, I want you to make a note of it. You see, most of our ideas on batteries actually came from primary cells. What do you have in a primary cell? You have things that are fully charged up, and over a period of time they're getting discharged. And so initially when people were looking at even the lithium-ion battery, they were looking at it with the same mindset. And it was very unsafe because both of these materials were quite flammable, this stuff. And so what was realized was that why do I need to do that? I will assemble my battery in the discharge state. This is my discharge state. My carbon is a perfectly stable material. The cobalt in the +3 state is very stable. I can hold these things in my hand. So I assemble the battery first and then charge it up. And can you imagine what it does in terms of production? That's what he says here. Achievement of a simple and efficient production process with no special atmosphere required for battery assembly made possible because LiCO2 is very stable in air, which means the discharge state, despite containing lithium ions. And the negative electrode is composed of carbonaceous material, which is also stable, this stuff. It's only when my carbon becomes negatively charged that it becomes very unstable. Okay, so there is a huge amount of work that is continuously going on the battery. And also remember that India has no supply of lithium. Our only lithium source is really all these spent, discarded, abandoned mobile phone and laptop computer things. If you can recover the lithium from that, that's great. You can recycle it. In fact, that's a big area. Otherwise, these batteries are hazardous materials. If you don't recycle, how will you dispose them of? Because you've got so many heavy metals in there. Last, let me also tell you that while everybody is going gaga about lithium-ion battery, 10 years from now, people might say, why lithium-ion battery? Use a sodium battery. Sodium is abundant. You've got so much sodium. Why are you bothering about lithium? So there will be huge amount of research on alternative batteries, and that work is already going on, which can be sodium battery, magnesium battery, fluorine battery, all kinds of battery. Okay, with that, I have come to the formal end of the course. Did you all understand? I went like a bullet train. Was it all clear?
Yes, sir.
Okay. Any other questions from anyone? Okay. If not, thank you.
Thank you so much, sir.
Thank you.
Thank you, sir.
Thank you, sir.
Yes, sir.